help, but she was just,
Not happening.
but she was we used to have a pretty rigorous placement method where you take a test and, sometimes it placed you incorrectly, but for the most part it was pretty good. And they don't do that anymore. You just pick what you want to take.
What?
It's like, they don't enforce prerequisites anymore here.
Okay, great. Nice to know. I'm going to go register for all the courses I can.
It reminds me when I first started here, there was this philosophy of students have the right to fail. I was like, well, shouldn't we be doing everything we can to put them in a class that they're most likely going to succeed in?
But if we succeed,
and now we're back
do
to
it
that.
all the first time, then no money.
No money. And now we're back to this again, where it's not required. Okay, so let's do these two, and then we're going to talk about some alternating series, because on the worksheet, that alternating series remainder was causing more trouble than any other problem, which I was kind of surprised at. So let's make sure that we understand that before the exam, because there's certainly one of those on the exam. So the last slide that we have in chapter 11 is just kind of a fun slide. We're going to come up with series representations for some numbers. So the square root of e is just a number. And if we want an infinite series representation for the square root of e, we go to the infinite series for e to the x and replace all the x's with 1/2. And so this will be an infinite series representation of this number. And of course, if you just wanted e to the 1, you would put in a 1 and you'd have 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. So whatever number you plug in for the x, that's going to give you the representation of e raised to that constant. So here, when we plug in the 1/2, we'll get a 1/4. So we'll get 1/4 multiplied by a 2 factorial in the denominator. And then here, we're going to get, let's see, when we plug in 1/2, we'll get an 1/8. And then we'll have a 3 factorial down there, etc. So that's how you can write constants as infinite series. You find the function that generates what you want. So we can now write this irrational number as a sum of rational fractions. All right, square root of e is irrational, but each one of these fractions is rational.
That's all we have to do for that kind of thing?
Mm-hmm.
Put it in.
Yeah, it's just kind of a, like,
Make the whole test that.
yeah.
Do it.
Here's number 1 through 5. What's that, Zach?
I have a question. Are there numbers that are so irrational they cannot be expressed by infinite series?
No.
It's gonna look
So a
good.
number is rational or irrational. You can't be so irrational. It's like, you know what I mean?
Since there's no numbers that can't be expressed by infinite series.
That's right. Yeah, you can find a representation for any number. It's hard. You can't.
Is there proof for that?
Yeah, we're not going to show the proof. We're not going to do the proof. But yeah, you can write when you get into analysis, which is first semester of analysis, you go back to the calculus book and you prove with epsilons and deltas every theorem you ever used in calculus.
Don't take analysis.
It's horrible, unless that's how you think. It's like 1 out of 100 math students actually enjoys that kind of thing. It's very rare. It's hard. So sine of 1, same idea. We're just going to plop in a 1. There we go, Zamboni. Perfect timing. So sine of 1 is that? That's it? That's it. All right, we're done with chapter 11. Too easy, right? Okay, so let's get to, so on the worksheet, the biggest issue was the alternating series remainder, and you have to understand that for the test. So let's go to some examples. Let's go to the review here, and I've got stuff here, but let's add a page, and let's do a couple. So the corrections for that worksheet are due on Thursday night. So that has been released. You should see it in your accounts now. Let's see. We'll put it at the top. So let's do some alternating series. And the biggest issue seemed to be with finding, a lot of you could find the k value, but not the number of terms. So let's make sure we understand. The k value is what the index value is that gets you to the term that is the remainder term. K is related to n being the number of terms that you need, but they're not equal to each other usually. They might be in some cases, but k and n are different. And you've got to be very clear on what is k equal to. Like if it says k is greater than 10, then you choose k equals 11. So k is a number, it's not an inequality. K is going to be a number. It is the term that is the error term.
Now if it's 10.5.
Then it's greater than 10.5, then it's 11. Because we're dealing only with integers as our counters.
So if it's 10.1, we're still going to 11?
Yep, because it has to be bigger than that.
Gotcha.
Right, so if you get k bigger than 10.1, you pick the first integer. It's true that k could be, if you end up with k being greater than 10.1, you could pick 50, but the idea is that we want the least number of terms, so we pick the first integer that would satisfy the inequality. And then we have to go figure out how many terms. So first we get k. Once we have k, then we have to figure out the number of terms. So let's go ahead and let's just look at the alternating harmonic for an example, because that's a pretty easy one to manage. So if we have -1 to the k, and let's suppose that k starts at, give me a second, let me think about it, and then this is going to be 1 over k. Let's start with 6 here. And let's suppose we want the error to be less than 10 to the negative, let's just go 10 to the negative 4. So we want the error strictly less, not less than or equal to, we want it to be less than 10 to the negative 4. So the first thing we have to do is figure out the k value where the term is less than 10 to the negative 4. And once we find the term, the first term that's less than 10 to the negative 4, we add everything in front of it. So let's just write out a generic representation here. So we're starting our counter at 6, so we're going to have an a sub 6, and that's an even number, which up here would cause a positive. So then we're going to have an a sub 7, and then plus a sub 8. So remember, for an alternating series, a sub k does not include the switch. So that's why I can write it like this. So there's a sub k. A sub k doesn't include the switch. So that's how it's going to be written out. Then we're going to have plus, minus, I guess, and then a bunch of dots. Let's figure out where we're going. Okay, so if we want the error less than 10 to the negative 4, we're asking ourselves, well, when is 1/k less than 10 to the negative 4? We want to know, when is that, what is the first k value that makes that true? So first we're going to rewrite this with, probably if we just do every single step. So 1 over 10,000. We cross multiply. So this says we want the first k that satisfies that inequality. So it's really important that you tell me what the k is. So this says that the first k bigger than 10,000 is that. So that's k. That is not n. That is not the number of terms that we need. So this says that's when k is equal to 10,001. So we're trucking out here. Keep on going, and we're going to get an a sub 10,000 minus a sub 10,001. So still the same pattern that if we have an even index, we put a plus. Odd index, we put a minus. And this just keeps on going forever. So when k is 10,001, this term right here, the magnitude of it, a sub 10,001, this is less than 10 to the negative 4. This is the first term that has a value under 10 to the negative 4. So that's our error term. This is gauging the remainder. We want to then add up everything in front. So we're going to add these. So we're going to add those up.
So 9,994.
So we have a couple of ways to do it. If we wrote out the summation notation, we would be going from 6 to 10,000.
It's 9,995.
Yeah, hold on one sec. Let me finish writing this and then we'll talk about it. So first, does everybody agree? We're starting at 6. We want to stop right there. We want to stop when k is equal to 10,000. So this is the partial sum that we have. So we had a couple of ways we counted this number of terms. You could say, so one way is that n, the number of terms, one way we said was that you could take the upper number minus the lower number plus 1. That does it. So this is going to be, we're going to subtract 5 from this, so we're going to get 9,995, which I think I heard. Or you could do something clever like this and say, okay, well, you could think in your mind that if you subtracted 5 from here, you would get to a 1. And if you subtracted 5 from up here, you would get to 9,995. And so that's the number of terms.
Why are you subtracting 5?
To get to 1, because if you have something like this, 1 to 10, how many terms is that? You're starting to count at 1. 1, 2, 3, up to 10 is 10 terms. This has 10 terms. So if you sort of think about creating an index that starts at 1, then this is the number of terms that starts at 1. If you go from 1 to 5, 1, 2, 3, 4, 5, you have 5 terms. So you can think about how do you get this how do you turn that into a 1, subtract 5? Well, if you take 5 terms away from there, you take 5 terms away from there, and you have 9,995 terms. So you can think of it that way, or you can do upper minus lower plus 1. So either of those two ways will tell us the number of terms. So either has what the heck? Has 10 terms. This has 10 terms.
The 10 side.
Right? Vanishing. And that's a 10, not a 16. And yeah.
So where did that extra 1 come from when you cross multiplied? K equals 10,001.
Because this is an inequality. This says k is more than 10,000.
Oh, okay. Sure.
So the first k value, k is always an integer, so the first positive integer bigger than 10,000 is 10,001. So we pick the smallest k that satisfies that inequality. All right, so let's try another one. Let's suppose, let's do -1 to the k. Let's suppose we have 1 over k squared, and k is going to start at, let's say, 8. Go to infinity, and let's suppose that we want the error
10 to the negative 3.
less than 10 to the negative 3. All right, so you all try that. So I'm first just going to write out the generics. It's always helpful to have a generic here. So a sub 8 is when k is 8. You could do some shifting if you wanted to. You could shift this whole thing so that that first term was a sub 0, or a sub 1 actually would be best because you're dividing by k here, so starting at 0 wouldn't be a good idea. But you could shift this so it started at 1 if you wanted. Let's write that down in a minute, just as a practice. So if we plug in an 8, okay, even indices are going to correspond to positive coefficients. So a sub 8 would be the first one, and then a sub 9 is going to be a negative in front, then plus a sub 10, minus, etc. That's going to go on forever. Now, a sub k, again, does not include the minus. It doesn't include the switch. So a sub k, we want that to be less than 10 to the negative 3. Well, yeah, let's just write it like that. We want to know when is it less than 10 to the negative 3. So a sub k is 1 over k squared. We want to know when is that less than 1 over, that's 1,000, 1 over 1,000. So we do the cross multiplication. 1,000 comes to the left, k squared goes to the right. We want to know when is k greater than the square root of 1,000? And somebody tell me what the square root of 1,000 is to one decimal point.
31.6.
31.6. So what does k have to be? 32. First integer above that. So this says k is greater than 31.6. So this tells us that k must be equal to 32. Again, that's not n though. That just tells us the index value when we have a term value under 10 to the negative 3. So if we start looking at these terms and look at the generic, that was a 32. So we're coming out here, we're going to have a 31. 31 is going to have a minus in front of it because it's got an odd index value. And then a sub 32, and then minus a sub 33, plus etc. All right. Well, when k is 32, a sub 32 is right there. So that is the first time that we have a magnitude under 10 to the negative 3. That's the first time. So that's the error term. That's the error on everything in front of it. So that tells us that we then want to add all of those. So those are what we want to add. So if we wrote it in summation notation, this would be the summation, negative 1 to the k, of 1 over k squared, and k would go from 8 to 31. Okay, so how many terms is that?
24.
So if we want to know the number of terms, if we want to just leave it in this form, it's 31 minus 8 plus 1. So we're going to subtract off 7. So what is that? Is that 24? Is that what you said?
Yeah.
So 24 terms. Okay. Now, if we want to do the re-indexing thing here, we can. We have to be careful though, because as soon as we write this, if we re-index to start at 1, we've got to change these k's. Like the k, if you change this k, you got to change them all. So if we were going to do this, we have to think algebraically. We have to replace this k with what, so that we could have a little algebra that would simplify to k equals 1. What would we replace that with?
K minus 7.
K plus 7. So k plus 7, if you replace that k with k plus 7, then you subtract 7 from both sides and you will get a k equals 1. So if we wrote this out like this, whoops, if we wrote it like this, we replace that k with k plus 7 equals 8. So that's going to mean, if we just reduce that, if we simplify that equation, it's k equals 1. All right. But now, when we want to come up with our upper value there, we have to think to ourselves, okay, well, the 8 turned into a 1. So we subtracted 7 to get to there. So now we have to subtract 7 to get to here. So we would have to do 31 minus 7 up there. If we do 31, if we do 8 minus 7 here, we have to do 31 minus 7 there, so we get the 24. All right. Now, if we're going to write this out, if we're not just thinking about the indexes of the indices, if we also want to write this correctly, we would have to come here and replace this k with k plus 7. If we turn that k into a k plus 7, all k's must become k plus 7. And then we would change this to be 1 over k plus 7 squared. So if we were truly re-indexing, this is what it would look like. And if you wanted to simplify it, this number up here is odd, right? So we could reduce that to just k plus 1. K plus 7 and k plus 1, it doesn't the only thing that matters is the parity. Is it odd or is it even? And so you could make it a k plus 1. But this would have to stay as k plus 7 quantity squared. And so from here, oh yeah, 24 terms. If it counts from 1 to 24, that's 24 terms. So there is our number of terms. And so if we wanted to use the S notation, partial sum notation, what would this be equal to? S sub what? S sub
24.
24. That's what this notation means. That says add up the first 24 terms. That's what S sub 24 means. Add up the first 24 terms. It doesn't mean add A0 plus A1 plus A2. It could if your index started at 0. This is generic though. It says sum up the first 24 terms. So all of these are different representations of the sum of the first 24 terms. So all of those could be represented as S sub 24. Doesn't matter. This index starts at 1, this index starts at 8. Doesn't matter. All we do is re-index it. We still have 24 terms. So that's how we could notate it.
So the exam, we should box k equals and then n equals?
Yeah, you want to make sure both are clear, which one's k and which one's n. Yeah. Because in general, they're not going to be the same. The only time they're the same is if k starts at 1. K starts at 1. It's the only time n and k will be the same.
Isn't it 1 less though?
Oh, actually, I said that wrong. What would it have to start at? So if k was 10, we add up everything in front of it. So if it starts at 0, then k is the number of terms in the partial sum. If it started at 0, because we have to do the subtract 1 thing. So that subtract 1 thing would, that one thing there, so in order to take care of that, a k would start at 0. Not subtract 1, add 1. Okay, so let's go and start doing the review stuff. So, same as it ever was. We just have a few questions. So, 12 to 15 questions coming from these sections. Just 2 chapters. Chapter 11 is kind of short. Again, in a lot of books, they just put this all in 1 chapter. Okay, well, overview. There's really nothing specific coming from that section because that just introduced us to sequences and series. You know, the real math started when we actually got into those details. So there's all our stuff from chapter 10. Chapter 10, all the way up through the root and the ratio test. So chapter 10 is the big one. There's a lot in chapter 10. Okay. So let's just start doing these. When we get down to the infinite series, I told you there would be 3 infinite series that you definitely needed to know. So when we get there, we'll talk about them. One of them is going to be e to the x.
No way.
It's shocker. Okay, let's do. We already spent some time, so I'm gonna pass on this one. I'm gonna try to stick to ones that are definitely much more important. Just because we already spent half an hour. So this one also caused a little bit of trouble using log limit process on the worksheet. Let's do this one. by using the shortcut. What is this going to be?
E to the 6.
So this is going to be e to the 6. It's not equal to, it's going to approach e to the 6. The limit of it's going to be e to the 6. So when we put that arrow, that sort of means as n goes to infinity. Technically, we might want to write that, but whenever you're dealing with sequences in series, you know that's what you're talking about, a limit at infinity. So that goes to e to the 6. It doesn't go to e to the 6x. It's a number. Right? There's no variable in what that limit is equal to. That limit is equal to a constant, e to the 6, not e to the 6x. Everyone got that? Christian, make sense? Yep. So no x in there, just a constant. Now this one, we could manipulate this. A couple of you manipulated this, but didn't show any work whatsoever. It's like, well, what did you do? Like, I need to see work. If you're gonna use the shortcut method when you're, one of the questions on the test is gonna ask you to do it with the log limit process, and you can't use the shortcut. But if you're gonna use the shortcut, you gotta put in some work here. It's not obvious what it goes to. You first flip this, and when you flip it, what happens to the exponent? It becomes negative. Right? When you flip a fraction, changes the exponent. 1/3 is 3 to the negative 1. So that is first step. And then we do the division here. We split the fraction with our fraction splitting skills called division. Now it's in the form where we can use the shortcut. The shortcut says this is going to have a limit that's equal to, so we didn't write the word limit over here, so we're going to put an arrow that implies limit. So this is going to go to e to the -3 multiplied by -4, so this is going to go to e to the 12th. Now, if we did it with the log limit process, here's what it would look like. So on the test where you have to do log limit, the idea is that you're first going to convert this over to a continuous function. So there's our function. That's our continuous function. And then we take the log of both sides. And when we take the log of the right-hand side, we pop the exponent down. And that's the whole point of taking the log. The log allows you to bring exponents down in front. And then we take the limit of both sides. And when we take the limit of the left side, the limit pushes inside the function because it can pass through continuous functions. Continuous functions are permeable. Now, over here, we are taking the limit as x goes to infinity. And so on the right-hand side, using a little bit of practice, we know we're trying to put the right-hand side into a form where we can use L'Hopital's rule. L'Hopital. L'Hopital. So when we look at this quantity here, natural log of x divided by x minus 3, that's going to 0. As x goes to infinity, the inside of the log is going to 1. Natural log of 1 is 0. And now we want the denominator to go to 0 also, so we take that coefficient function and we do this. All right, 4x is the same thing as division by 1 over 4x. Dividing by 1 over 4x, multiplied by the reciprocal, which gives you 4x. So those expressions are equivalent. This is now in L'Hopital's form. So we know that we can apply L'Hopital's rule. And L'Hopital's rule conceptually is really simple. If you have a fraction of functions, it's going to approach the same thing as the fraction of derivatives. Which makes perfect sense because the derivative is the best approximation for the function. If the derivative is the best approximation, the quotient of best approximation should approach the same number that the quotient of functions approaches. Otherwise, it wouldn't be a good approximation. So now we want to apply L'Hopital's rule. So we differentiate numerator, differentiate denominator. Derivative of a log, 1 over the inside. We reciprocate the inside. So 1 divided by the inside. In other words, flip it. 1 over the inside times the derivative of the inside. The inside's a quotient, so we have to use the quotient rule. Low d high minus high d low. So low is x minus 3. D high, the derivative of that single x up there is 1. So low d high minus high. Oh, d low is also 1. All divided by low to the 2, low squared. So there is the quotient rule. Low d high minus high d low over low squared. And now we have to differentiate this. So the 4 is a coefficient. You can think of that 1 over 4x. I would think of this like that. Right? The 4 is in the denominator, and it's not affected by the exponent on the x. So if you wanted to differentiate this, the 4 stays in the denominator. This is going to be minus 1/4 x to the negative 2. Exactly. And so we could write this as negative 1 over 4x squared. So that's going to be a good way to write it as a fraction, because then when we divide by a fraction, we multiply by the reciprocal. So now we multiply by the reciprocal. So we're going to have limit. Let's not cancel anything out yet. Let's just try to be super careful, because I just see so many mistakes on this. Yes, the x minus 3 was going to cancel there. Let's do it in a minute. Let's first focus on simplifying this numerator. What does that numerator simplify to? Negative 3. Exactly. Does everybody see that? X minus 3 times 1 is x minus 3. Minus x times 1 is minus x. So we have x minus 3 minus x. So x minus x is 0, minus 3 preserved. So we have that. And now we have to flip this fraction. Dividing by a fraction means multiply by its reciprocal. And so you can write this in a couple of different ways. I'm just going to keep the minus attached to the negative 1 to the 1 there. That's probably the simplest way, just to keep everything straight. Now let's cancel. Okay, first let's look at these guys. Let's look at the x minus 3's. So we are going to be left with 1x minus 3 in the denominator. Tell me if you don't agree. So one of those. Now we look at the x's. We're left with 4x in the numerator. Right? One of these x's is canceling. So 4x. The minuses cancel each other out. So we have 4x times 3, which is 12x. So that's where it's all boiled down to that. And the limit of this, we don't even need parentheses in the denominator, do we? And what's the limit of that?
12.
12. Limit of that is 12. And so on the other side, we have natural log of limit of y as x goes to infinity. Our whole goal was to solve for this thing. We want the limit of y, the limit of what we started with. We let y equal what we started with. So we exponentiate both sides. So this tells us that we end up with limit of y is equal to e to the 12, which of course is the same thing that we got for the shortcut. All right, let's see. Let's go to another limit. These are quick and easy. What's the limit of this first one?
Infinity. Oh, wait. Oh.
What's that limit? So we know our basic concepts are if we take a fraction, a real fraction, a number less than 1 in magnitude, Could be positive or negative. And that's going to go to what then?
5, 6. Like negative 5, 6?
No.
No, I'm not doing math right.
No, not doing math right. Not yet.
Yeah.
Swing and a miss. What was that? Raise? 0.
Oh, right, goes to 0.
Right? The magnitude of this base, the magnitude is 2/10, a fifth. That's less than 1. If the magnitude is less than 1, the limit of this is 0. So the limit as n goes to infinity is 0. All right? Doesn't matter if it's positive or negative. If the magnitude is less than 1, so in other words, if the fraction is between -1 and +1, that limit is 0. How about this one?
Infinity.
Yeah, infinity. All right, as n goes to infinity here, the base, so this was the base, this is the base. If the base is less than 1 in magnitude, it goes to 0. If the base is bigger than 1, it goes to infinity. Let's just do a quick squeeze theorem one. So the idea with squeeze theorem, let's do the inverse tangent one, is that you first start by bounding the function that's in the expression. So if we have a bounded function, like inverse tangent, it would also be technically correct to put equal to here, right? That's not changing anything. Tangents between it. And we kind of know that with these squeeze theorem ones, we end up with a compound inequality where the left expression and the right expression match. And so putting the equal to sign might feel more reasonable in the end because those numbers are going to be the same. But this is true, right? Certainly you don't need to put equal to, but this is true. If it's less than pi over 2, it's less than or equal to pi over 2 also. And then we do division across the board to make the middle match. And then we take the limit. So we're going to take the limit of all 3 pieces here. So we're going to end up with negative pi dividing by 4n over 1 means multiply by the reciprocal, so we get an 8n in the denominator. Same idea here. We're going to take the limit. This is what we're trying to figure out. We want to know what's the limit of this expression. And then on the far right, same thing. We're going to take the limit of that, multiply by the reciprocal of that, and we get pi over 8n. And these limits are all as n goes to infinity. So what do we see on the left and the right side?
0.
Yeah, those all go to 0. So we have 0 less than or equal to that, less than or equal to 0. So our conclusion is that the limit of arctan of n over 4n is equal to 0 as n goes to infinity. And that's kind of, we've talked about the intuition behind this. We know that if the numerator is constant and the denominator is growing without bound, we know those fractions are going to 0. So the extension of that is, well, maybe we don't have a numerator that's constant, but if we have a numerator that's bounded, and so it could be wobbling around like sine or cosine, or it could just have horizontal asymptotes like arctangent. If the numerator is bounded, it can't go above a certain ceiling, yet the denominator is increasing without bound, the fractions have to be squishing to 0. They've got to be going to 0. If the bottom's getting arbitrarily large, and the numerator can't get bigger than pi over 2, those fractions are going to 0. So that is a pretty reasonable thing to get conceptually. How do we prove it? We just use the squeeze theorem. So the squeeze theorem is to justify this idea that a bounded function divided by something going to infinity will create a limit of 0.
It's like nasty.
Yeah, it's quick and it's easy though,
So
right?
for the sign, it'd be like 1,
So the sign is bounded. What are the bounds on sign?
-1 and 1.
-1 and 1. So we would start with that.
And then you put the 2n underneath.
Then we divide by 2n, and then we take the limit, and the outer limits are going to both be 0. Yeah, exactly. Correct. Yeah, so then we'll do that. And then when you take the limit, you'll get a 0 on the left and a 0 on the right, so the limit of the middle has to be 0. Okay. Recursive. Let's not do that one unless we have time. Geometric, that's super important. So for a geometric series, we have two different things that we should have in our mind. First, when it converges, and then second, what it converges to. So, for a geometric series, we have an R, common ratio, and we have an A, the initial term. And for a geometric series to converge, what's true about R?
Must be less than 1.
So if the magnitude of R is less than 1, then we have convergence. Otherwise, we have divergence. So less than 1 in magnitude. Could be negatives. The first step here is to rewrite this so that it's in our standard form for a geometric series. The standard form for a geometric series is a r to the k. And usually they start at 0. They don't have to, but usually they do. So in other words, the key feature, the defining feature here, is that the k is all by itself up there in the exponent. Not minus k, not 2k, not k over 5, right? Just k. So we need to peel this k away from that minus 2. And we know that laws of exponents satisfy this. We know that if we have a power raised to a power, you would multiply them. So if we just break that apart and create a second exponent, there we have it. And we can simplify that quantity that's in here, 3 to the negative 2, is a ninth. So here we've rewritten that series and put it in the standard geometric form. Now it should be obvious what the two important values that we need to identify are. What is the A value?
1.
1. The A value is the initial term. The initial term is found by looking at the initial index. Well, the initial index is 0. 1/9 to the 0 is, in fact, 1. And what about the common ratio? So the common ratio is the base in the exponential expression where the k shows up. And so it's whatever's right below the exponent. Once we get that exponent isolated, so it's just k, then r's right there. And then for the sum of a geometric series, the sum is equal to a over 1 minus r. If it converges, if it doesn't converge, the s equals a over 1 minus r is rubbish. We only go here if it converges. This is less than 1, which means converge. If that's bigger than 1, a couple of you on the worksheet just wrote that even a divergent series converged to something. All right, so we only use this formula if we have convergence. Otherwise, this is giving us rubbish. So we know it converges because magnitude is under 1. So this is going to be 1 over 1 minus a ninth. Multiply everything through by 9. We'll have 9 over, or I guess we could, lots of ways we can do it. 9 minus 1, so we get 9/8. So if you only do the capital S, the sum of the series, only if it converges. If it doesn't converge, that S is meaningless. It's rubbish. And once again, right here, it seems like a geometric series, but we want to put it in the geometric series form. So we want to peel off this k. We want just an outer exponent of k. Why did I do 2 with the same exponent? So this here, what is going to be the base? Can we do that base in our head? 1/4 to the negative 2?
16.
16. All right, the negative 1 flips the 1/4 into a 4, and then 4 to the 2 is 16. Okay, so this tells us that a is equal to 1 and r is equal to 16. Does this converge? This is greater than 1, therefore diverge. So you do not do this. You don't say s is equal to 1 over 1 minus 16 and get this rubbish. These are all positive numbers. You have 1 plus 16 plus 256 plus blah, blah, blah. That does not equal negative 115. Right? Adding up these huge positive numbers does not equal that.
Is that where the mistake came from, thinking the all real numbers add up to negative 112?
Mm-hmm.
Alright, all integers?
Mm-hmm.
That's where that mistake
Exactly.
came from?
Yeah. Yeah, the sum of the sum formula is being misused. Violation. Violation. So uncool. All right. The one here, everything is kind of jumbled together there. We need just a k as the exponent. So what we want to do is unravel. So first, algebra 1. Is that minus sign affected by that exponent? No. The only way a minus is affected by an exponent is if that minus is wrapped up like a Christmas present with little parentheses. If that minus is just hanging out in front, it's not touched by that exponent. So this is going to be minus 1 multiplied by 2 to the k multiplied by 2 to the negative 3. That's how we would break that all apart. Laws of exponents say you add exponents when you have a common base. Okay, well, we're just doing that common base backwards, right? Common base here is 2. Add those exponents, we would get back to there. This one, we're going to have a 3 to the k multiplied by 3. So there we have it. All right, so now let's try to collect all the constants. So the constants can all come out to the front, right? They can come all the way out to the front. In the numerator, we have a negative 1, 2 to the negative 3. That shoves it into the denominator as a 2 to the 3. 2 to the 3 is 1/8. Multiplied by 3 is 1/24. So that is what we will have for the constants. And then when we look at the powers of k here, those are now matching, and so that's going to have a base of 2/3 raised to the k power, and this one's starting at 0. All right, so now we have it written in the standard form of a geometric series. We can identify the two important constants. What is a?
Negative 124.
So, and here's where we have a choice. We can sort of include the negative 1/24 or not. We could just focus here. Doesn't matter. Either is totally correct. You could say that for the series part of it, you could say that a is just 1. Or if you want to include it, totally fine. Doesn't matter. And then r is 2/3. And does this converge or diverge?
Converge.
So that is under 1, so therefore converge. Now when we go to find the sum, we absolutely need that negative 1/24. That negative 1/24 affects the sum. It doesn't affect convergence or divergence. So we can have negative 1/24 and then a over 1 minus r. So this will all end up being negative 1/24. That's going to be a 3 right there, so we get negative, let's see, 1/8. So that is the sum of this geometric series. We just want to think for a minute. Does that make sense? Well, yeah, that makes sense that we get a negative because this negative is just a multiplier out in front. The series part of it that I have boxed is definitely positive. All right, this is all positive stuff, but then you multiply by a minus to get a minus. So let's do a telescoper. So telescoping is the other series that we can find S. There's only two. Geometric and telescoping, those are the only two that we're finding S for. All the other ones, we're being ambiguous. We say, hey, it converges. What does it converge to? I don't know. All right, we're being a little ambiguous. But geometric and telescoping, we can be very specific. So the first thing we would like to do is, on the exam, I will tell you that it's a telescoping series, but we still have a little work to do here. We would have to first factor the denominator. And then a telescoping series always has this form where it's a fraction minus a fraction. What technique do we use to break that apart? So we want to use PFD. So we take this fraction, factor it, and then we know that it's going to be A over K plus 1 plus B over K plus 3. So that's how we would break it apart. Multiply both sides by the common denominator. And we've done enough of these, hopefully, that this process is pretty fast. And then we're going to use convenient values. So -3. When we use k equals -3, we plug it in across the board, so we're going to get 2 equals -3 there gives 0, there gives -2b. So b is -1. So we plug it in for all the k's. And then our next convenient value is -1. So we replace it for all the k's. On the left we still have 2, -1 there gives us 2a. -1 there gives us 0, so a is 1. So that tells us that we can rewrite this as a over k plus 1. So that's 1 divided by k plus 1 minus b, so 1 over k plus 3. There's our telescoping series form. All right. Any questions with the PFD? Convenient values, quick and easy by this point. All right, so now what we go back to is the concept of the convergence of an infinite series. An infinite series converges if the limit of the sequence of partial sums exists, if it's a number. So we want to find the sequence of partial sums. We want to find S sub n. That's the sum of the first n terms. Okay, so we start plugging in. Our very first term is going to be 1 minus a third. We start at 0, so we have that. And then we go to a k value of 1. So we're going to get a half minus a fourth. So let's say this is k equals 0. This is k equals 1. Next one will be k equals 2. So k equals 2 is usually far enough. So now we're plugging in a 2 there. So we get a third minus a fifth. Then we're going to get some stuff in the middle. Okay. Now once again, n is the number of terms. Here, n is 1. This is, and maybe I'm going to use a different thing than n because that n is right there. Oh, that's okay. We can use n. Sometimes I use the number symbol. Doesn't matter. So the n value, it's, as long as you think about when n is 2, you're adding up these first two terms. So when n is 2, we're adding up those two terms. S sub 2 is the sum of the first two terms. Okay, so the number of terms here is 2. Now the number of terms here is 3. S sub n means the sum of the first n terms. So we have to get our k's correct. when we look at our last two terms, what should the last two k values be?
K equals n minus 1, 2.
Everyone agree with that?
N minus 1, n minus 2.
Does everyone agree with that? So if we're starting our counting at 0, we can't end at k equals n because that will have one extra term in it. So if we want the first n terms, there's the first term, there's the second term, there's the third term. When k is n, we've got one extra term. So we're looking at the two terms prior to k equals n minus 1 and k equals n minus 2. So we come over here, plug in n minus 2, n minus 2 plus 1 is n minus 1. So 1 over n minus 1 minus, plug in n minus 2 here, negative 2 plus 3 is positive 1, so we have 1 over n plus 1. And then our very last term, our nth term, so our nth term, this is going to be the n minus first term, and this is going to be the nth term. That's why I don't like using the n there. I'm going to put number here instead. So the number of terms. First term, second term, third term, n minus first term, nth term. Just looks better. Okay, so plug in the n, you get 1 over n plus 1 minus 1 over n plus 3. So there's S sub n. That's what I'll need to see, your S sub n.
Isn't it n minus 1, not n plugging in? So it should be...
Oh, I'm not plugging in just n. Thank you. Yeah, I just plugged in n. So if you're plugging in n minus 1, that's going to be just an n in this denominator and an n plus 2 in that denominator. Okay, now the cancellation pattern. We start on the left, figure out what it looks like to move to the right from the left, and then we reverse it and move from the right to the left. So when we look here, let's see. Okay, there's a jump. So the first term, the first part, if we think of this as the first term and it's got two parts, the first part cancels with nothing. The second part of the first term cancels with the first part of the third term. So there's a gap. So second parts are going to cancel as we move to the right. This first part is not canceling with anything down here that we can see. So that's going to stay. This, if we wrote one more term, we would see that this first part is going to cancel with a second part over here in the muck in there. So the terms in the front that are going to be preserved, the numbers in the front that are going to be preserved are those two. And this is usually the pattern. If the difference between this and this is 2, usually you get 2 in the front and 2 in the back. Now when we go right to left, our cancellation looks a little different. So if we look right here, when we go right to left, first part is canceling with second part. So when we're going right to left, the first part is going to cancel with something over here in the muck. And this first part is going to cancel with something over there in the muck. So the stuff that's preserved at the tail will be that and that. And so our simplified form for S sub n will be 1 plus 1/2 plus, nope, minus 1 over n plus 1 minus 1 over n plus 2. So that is S sub n.
Will you go over how to get to 1 over n minus 1 again? To get to those.
That one right here?
Yeah, just to get to those terms again.
So to get to these terms, to get to this term with these two parts.
I get how to get to it, but how do we get to k equals n minus 2?
That one there and that one there?
Yeah.
So if you want 5 terms and you start at 0, what is that last index value? If we want 5 terms, 1, 2, 3, 4, 5, but if we start counting at 0, 0, 1, 2, 3, 4, we want the last index value to be 1 less than the number of terms.
Okay.
So if we're starting at 0, we want the last index value to be 1 less than the number of terms.
Okay.
So S sub n means n terms. But if we start counting at 0, that means we want the index value to be 1 less than n. And then the term before that is 1 less than 1 one less than that one, so that's n minus 2.
Okay.
Right, and then this one would be n minus 3, n minus 4, n minus 5.
So is the difference between your initial K and your number of yours? Or and your N1, I guess. So
In this case, yeah.
it's K initial minus 1.
K initial minus 1, yes, exactly.
Is what you're.
Yeah, so if this one started, if we started with, say, k equals 5 here, and this is this, these are just our k values, so this is if. So if k started at 5 here, then k equals 6 would be here, then k equals 7 would be here. And if we wanted n terms, we're looking right here, we're starting our counting at 5. If we want n terms, what are we going to want?
4. N plus 4.
So this is going to be k equals n plus 4. This is going to be k equals n plus 3. Let's check. If we subtract 4 from here, we'll be at 1. If we subtract 4 here, we'd be at n. So then it lines up, right? Because if we count from 1, n terms is 1 to n. So if you subtract 4 from there, you're at 1, and you subtract 4 from there, you're at 1. Just like here, if you add 1 to 0, you add 1 to that, and you get to n. So yeah, so that's how we have to do it. It's a little complicated, but. So there is our S sub n. Now we can find, so you're going to have to find S sub n. And now we want to find S. S is the limit of S sub n as n goes to infinity. And what is that equal to? 3s. So we can find the sum of the series if the series is telescoping.
Do you care if we combine the first two terms on our S and N?
No.
Okay.
Yeah, you can write that as 3s.
So if we do or don't, it's pish posh.
Pish posh. Pish posh. Okay, let's go ahead and take a 10-minute break. And then we'll do some DTs. Did I hit record?
Yes.
Okay, good. Oh, for a second there. Can the divergence test give you convergence?
No.
Never. So the divergence test has 2 results: diverge or inconclusive. Those are the 2 results. Diverge or inconclusive. So with the divergence test, we are taking the limit. Where's Dustin? He totally blew this one. We need him in here. So we're taking that limit. You pay attention to this.
Yes, sir.
So we are taking the limit of a sub k. Right? We're not saying that this series is equal to a number. We're taking the limit of a sub k. And if the limit of a sub k is 0, our conclusion is inconclusive. If the limit of a sub k is not 0, our conclusion is diverge. So if the limit is 0, we have to do more work. It's inconclusive, right? It doesn't converge. And with the divergence test on the worksheet, it wasn't asking you to find the sum of the series. If we're just applying the divergence test, those are our only 2 results: diverge or inconclusive. So when we take this limit here, right now it's in an indeterminate form. It's in L'Hopital's. We can use it's in L'Hopital's form, infinity over infinity. And so we can take the derivative of top and bottom. So the derivative of the numerator is 1/2 k to the minus 1/2. The derivative of the denominator, it's a log. 1 over the inside multiplied by the derivative of the inside. So that's 1 over 2k times 2. So that derivative is just going to be 1 over k. So let's simplify this. So we have limit. So here we have a 1 in the numerator, 2 in the denominator. Here we have a 1 in the numerator and a square root of k in the denominator. Here we have 1 over k, but we have to flip it, so we get k over 1. So now we have that. This can be simplified to, let's see, we end up with square root of k in the numerator and a 2 in the denominator.
Why is square root k in the numerator?
You tell me.
Wouldn't two cancel out?
You're multiplying.
Well, that's division right there. If you have one full k up top and you have half a k down below,
Oh, so you simplify it even further.
so it's k to the 1 over k to the half. K to the 1 minus a half is k to the half. Or you can think of the numerator as a k, which is square root of k times square root of k. Do you agree? If you think of k as root k times root k, one of the root k's cancel.
I thought we had to do another L'Hopital because I was thinking k over just square root of k.
Makes sense now?
Yeah.
And then what is that limit? Infinity. So what's our conclusion?
Diverges.
Diverges. So this is greater than 1, therefore, greater than 0, therefore diverge. So our only two conclusions are diverge or inconclusive. So same idea here, we're going to take the limit of a sub k. So we're taking the limit of this as k goes to infinity. All right, and the way we manage this when we have square roots is that we need to have a pair of them. In order to evaluate this effectively, we want that. That's how we evaluate a square root. We create two of them so that we can then do this kind of thing and push the limit inside the square root. So what goes inside the square root down here? We could FOIL it, but let's just write it first as the square root of k cubed plus 1 squared. Right, the square root of the square, they undo each other. They're inverse operations of each other. So now we can get to the inside of the square root. Now let's FOIL it out. So that's going to be k to the 6. What's the middle term going to be?
2k cubed
2k cubed
plus 1.
plus 1. And what's that limit? 0. Couple of ways you can get to it. You could divide everything by the highest power of k. You could divide everything by k. There's a couple of strategies, or you can maybe do it by inspection, depending on what you're thinking in your mind. So if you divide everything by the highest power of k, so if I go through and divide everything by k to the 6, that's what I end up with. And all of these little fractions are going to 0. So we have 0 divided by 1, which is 0, and the limit of a constant is itself. So we end up with square root of 0, which is 0. And what's our conclusion then?
Inconclusive.
Inconclusive.
Converges.
Maybe.
Inconclusive. Maybe it converges, maybe it doesn't.
So instead of writing equal signs everywhere, you prefer arrows or something?
Well, if things are equal, you should use the equal sign. If you're saying something implies something, then you use an arrow.
Okay.
So like here, you don't want to put equal.
Who would do that?
Not someone that is clueless.
That's true.
Yeah, so we would put equal next to that summation if we were actually finding the sum of it.
Yeah.
You know, so what are the only two series that we really should be putting an equal after? Telescoping and geometric, right? Those are the only two that we really are finding S. Right? Those are the two that you technically can say equal to. Like here, we're taking the a sub k and we're finding the limit of a sub k. So it's not that we're, finding the sum of the series. we're taking the a sub k and taking its limit and then making a conclusion based on the value of the limit.
Would putting an arrow there be okay?
Yeah, putting an arrow here would be fine.
Okay.
Yeah, you could absolutely there, it's totally legit.
I just don't like math like floating around, so I like to.
So you just get rid of everything and.
I just put equal signs everywhere.
Yeah. I mean, we use the equal sign in different ways too, unfortunately. We use the equal sign, in the old days, we actually used to use a couple of symbols. Like if we were gonna define a constant, a variable to be equal to a constant, we used to do something like that. And we would reserve an equal sign if it was an equation that you would then solve. So you kind of knew, oh, I'm defining x to be 2. I'm saying the value of x is 2 versus this is an equation that has two expressions equal to each other that you can then, now you can manipulate both sides versus, that sort of directional thing. But now we just use the equal sign for a million different reasons. Okay, that takes us to the ratio test. So when we use a test, we need to know a sub k. Right? All of these tests involve a sub k. We take the limit of a sub k for the divergence test. We take the limit of the ratio for the ratio test. We take the limit of the kth root for the root test. If we do the limit comparison test, we need a sub k. If we have a series that's in expanded form, we need to figure out what the a sub k is. So let's just see if we can do that here. So what are we noticing here? Are you noticing in the denominator that you have powers of 6? The denominator is a little easier to sort of notice that that's a 6 to the 1, that's a 6 to the 2, and then if you check on your calculator, you should see that we have those things. Okay, how about the numerator? What do you think we have in the numerator? So, what if we think about powers of 2, what is the, oh, but that's not a power of 2.
But it might be.
It's 2
K
times.
To the something?
Say that again?
K to the something?
Yeah, exactly. So this is 2 to the, is that 2 to the 5th right there?
Yeah.
And this is 3 to the 5th?
Yep.
And is this one 4 to the 5th?
Sure.
4 to the 5th, so 4 times 4 is 16. 16 times 16 is 256. 256 multiplied by 4 is 1024. Okay, so then we could say, oh, this is 1 to the 5th. So we're going to think of that. So this is going to allow us to build the a sub k. All right, so our summation then. Let's start at k equals 1. Seems reasonable. So then we're going to build this. So this is going to be 6 to the k in the bottom. Everyone agree?
Yep.
And then the numerator is going to be k to the 5th. Okay, so there is our series in summation notation. So this form here is called expanded. Sometimes this is referred to as closed. We'll call it summation notation. The a sub k is right there, and we are going to use the ratio test. Okay, we want to know if that converges or diverges. So we're going to use the ratio test. So the ratio test says take the limit as k goes to infinity of the absolute value of a sub k plus 1 over the absolute value of a sub k. So the ratio of consecutive terms. Ratio of consecutive terms. So in your mind, you're envisioning regardless of what you start at, you're sort of thinking about this. This is your sequence of terms. And you're thinking about this divided by that. So it should be a proper fraction. If those terms are going to 0 and they're all positive, in our minds, it's easiest to think of them as, these as proper fractions, if it converges. Okay, so we take our a sub k. We have to turn all the k's into k plus 1s. And then we divide by a sub k, which means multiply by the reciprocal of a sub k. So we have that. And then we want to simplify this. So the first thing we see is that there's one extra k in the denominator. So we're going to sort of pair the powers with base 6 and pair these polynomial things. So I'm going to do this with the polynomial things. And then I'm going to put a 1/6 like that for the common base. So we have that. And this limit is as k goes to infinity. And so what does that limit equal to? 1/6. Everybody agree that this part here goes to 1? So the limit can climb inside there. Limit can pass through continuous functions. The squaring function is or the power of 5 is that's a continuous function, so it can go inside the limit of this ratio. Powers match, coefficients. Fraction of the coefficients is 1. 1 to the 5th is 1. Okay, so there is our limit. How do we conclude the ratio test?
Like a geometric.
Like a geometric, so less than 1 is converge. Yep, so ratio and root, cousin of the geometric series, less than 1 is converge.
So it converges to 1/6.
No,
Or not.
it does not converge to 1/6. So we don't know what the sum of the series is. As long as this limit is less than 1, we know the series converges, but it doesn't tell us anything about what it converges
You
to.
can't find the S.
We cannot find S here because it's not geometric and it's not telescoping. So the only time we can find S is geometric or telescoping. And this is just telling us that the terms are going to 0 fast enough. That's what that's telling us. But it's not telling us what the series converges to. Well, let's try a root test. So root test is good if you see a big power of k on the outside. And so we're going to take the limit of the kth root of all of this. So the kth root of all of that, we're essentially dividing that exponent by k. We're going to cancel out a common factor of k. So that's going to leave us with, if we divide out a k, that leaves us with that exponent. And this is an indeterminate form. This is the indeterminate form, 1 to the infinity. That is the one that's on the worksheet. It's the one that leads us to E. That is the indeterminate form that creates all the E magic. So this question is just evaluating this limit. It doesn't say use the log limit process. So we can use the shortcut. Okay, so to use the shortcut, the first step is that we want to flip the base. And we flip the base so that we can then split the fraction. We can't split a fraction unless the denominator is a single term that can then be shared with the numerator. We can't split that. You can't split when the denominator has 2 terms. So we flip it over, we turn the exponent negative, now we split the fraction. Now that the fraction is split, we can use our shortcut, and that limit is equal to e to the negative 20. So we do e raised to whatever that number is, multiplied by that number. E to the negative 20. And our conclusion?
Less than 1.
That is less than 1. Therefore converge. Less than 1 converge. Less than 1 converge. All right, let's do a comparison test. So on the test, I'll tell you which test to use. So let's use the comparison test. remember that our basic rule of thumb is that to find the series that you want to use as your comparison series, you essentially are eliminating from A sub k, so A sub k is the series that we're analyzing. We essentially eliminate any extraneous stuff, any insignificant stuff. And when we look at this, the fourth root of k, the bird wing in quadrant 1, it's growing very, very slowly. K is the identity function, y equals x. That's growing much faster than that bird wing. So in terms of insignificance, we're thinking of the fourth root of k as being insignificant relative to the rest of the denominator. So we have two choices here. We can let b sub k be 1 over 5k, or we could just do 1 over k. It kind of depends. We've seen a few examples where leaving the 5 in was more helpful. It helped with the inequality. So why don't we just leave it in and just see what happens? So let's leave it in. Does that series converge or diverge? So this diverges because it's what? If we factored out the 1/5,
P series with P of 1.
yeah, this is a P series of P is 1, or it's a harmonic. So either way. So P is 1, therefore diverge. Because for a P series, P has to be what to converge?
Greater.
Greater than 1. So opposite of the geometric series.
Would you allow us just to say biharmonic series?
Yep, or you could just say diverge, harmonic series. Absolutely, either way. So now we know that that diverges, so we suspect that this diverges. So we want to show, well, let's see, is it bigger than diverging diverges or less than diverging diverges? Bigger. So we would want to show this. If we can show that the A sub k's are bigger than the B sub k's, then the A sub k series must also diverge. If it's bigger than a diverging series, must diverge. Okay, so let's see if we can show it. So we don't know. Is it going to be true? That's what we want to show. Multiply both sides appropriately, aka cross multiply. Whatever the algebraic notion in your head is that allows you to do that. And then we subtract off the 5k's. So we have 0 less than or equal to fourth root of k with a negative in front.
0 greater than.
So yeah, the way I wrote that almost makes it feel like that. Let's move that over and make that a little more distinct. So negative fourth root of k, is that true? Yeah, fourth root of k is a positive number. Right, fourth root of k is a positive number, and if you multiply it by -1, that forces it to be negative. So this is now true.
So it does diverge.
So therefore, both diverge. Yes. So the comparison and the limit comparison, both are going to do the same thing. So if you chose your comparison series to be a divergent series, then the original diverges. If you chose the comparison series to be a convergent series, and you get that limit, then both converge. Okay. Alternating series test. Let's not go through that one. It's important to know, but we've done it so many times, I think. We have two steps. The limit of a sub k has to be 0, and the sequence of a sub k has to be decreasing. So I want to make sure that we get to some of these IOC type ones. All right, let's take a look at this. So find the radius and interval of convergence for the following power series. So radius of convergence, we have two choices with a power series. So as soon as we use the word power series, notice that that's when the x's appear. Otherwise, it's just a series. So a series has numbers. A power series has x, powers of x. That's why we call it a power series. So we can use root or ratio.
It's specifically x to, like, varying powers, it can't just be x for everything, right? Like, it can't just be x to the first one.
It's got to be power, yeah, varying powers, integer powers, positive integer powers. There can be gaps in it, but it has to be positive integer powers that are getting bigger. So we could use the root or the ratio test, doesn't matter. Often with the power series we use the ratio test most of the time. But here we've got a power of k. So let's go ahead and use the root test. So we take the kth root of the absolute value of a sub k as k goes to infinity. All right. Well, when we take the kth root of that, we're left with 8k absolute value of x. We don't need the absolute value symbol around the 8 and the k because those are positive. All right. Now, this limit is as k goes to infinity. The 8 and the absolute value of x have no k in them. So let's just factor them out. And now the limit of k as k goes to infinity. Infinity. So this is infinite. When is that less than 1? Never. So the only place it converges is, yeah. So therefore the interval of convergence is, the radius of convergence is 0. The radius of convergence is 0. And the interval of convergence isn't really an interval, it's just the center of the series. And we know that every series converges at its center because all the terms disappear except possibly the first term. So a series always converges at its center. So this is never less than 1, so the radius is compressed down to just 0, and the interval is just a single point. If you plug in 0 here for all k's, it's actually pretty boring. It just all turns into zeros, right? That series is equal to 0 when x is 0. This one we'll use the ratio test. So we're taking the limit of the ratio of consecutive terms, absolute values. So we always start with a sub k plus 1. That's in the numerator. Just think in your head that should be smaller over bigger. The series, if it converges, the terms are getting smaller in magnitude. So we're putting the smaller one over the bigger one. Right? It's progressively getting smaller if it's converging. So limit, let's see, a sub k plus 1. So all of the k's get replaced with k plus 1. And then we need absolute value. We don't need it in the denominator because that's always positive. So there's a sub k plus 1. Dividing by a sub k means multiplying by the reciprocal. So we're going to have 2x to the k. That's absolute value though, because x could be negative. Don't the 2's just cancel? Those just cancel. That 2 is not part of the exponent. It's just a coefficient. So that just cancels. The k factorial simplifies to how much where?
K plus 1 denominator.
K plus 1?
K plus 1.
K plus 1 in the bottom?
Or is 1 over k plus 1?
Agreed. And it looks like the x's, how about the x's?
1x is equal.
1x up top, have to keep the absolute value, could be negative. So that is what it simplifies to. And once again, this limit is as k goes to infinity. I don't see any k's in the numerator. So absolute value of x can come out to the front. We have the limit of that. So this limit is equal to 0. When is that less than 1? Always. So this is less than 1 always. So therefore, if it's less than 1 always, the radius of convergence is infinity. And convergence is for every single possible x. So the interval of convergence is going to go from negative infinity to positive infinity. It's always less than 1. Doesn't matter what x you plug in. If you plug in x equals 5 million, 5 million times 0 is 0. So it doesn't matter what you plug in for x. It's always true. All right, this one is going to be super similar. Let's do some other stuff. So let's look at composition. This tends to be, well, not this one. 2 down, that's our hard one on this test. Yeek. Okay, so use geometric series to find power series representations centered at 0 for this. So 1 over 1 minus 6x. We want a power series for that. Well, we know power series for 1 over 1 minus x. That's the geometric series. And what are we doing? What are we replacing that x with to get to this? 6x. So that's what we do. We're going to come in here and we're going to replace this x with 6x. So we're going to have 6x quantity to the k still starts at 0. So that is our new power series. Anytime we have a power series, we need to know what its domain is. So we have to come over here and fiddle. So this is what it started out as. But if we replace the x with 6x, we now need to solve that inequality and figure out what the new interval of convergence is. So we divide through by 6. We do not need to test endpoints when we do a sub. That's one of the nice things. We're done. That is the new interval of convergence. We don't have to do any endpoint testing. So whenever we can avoid endpoint testing, we want to do it. We could test the endpoints, but
Will you give us that on the test? Where it says geometric
Yes.
series? Okay.
yeah. Another one like this. So there was 3 in this theorem. One was substitution, composition. One was this multiplying by a power. And if you multiply by a power of x, let's see, okay, we've got this power series given to us. All right, it's given to us. And we want a power series for p of x. What's the only difference?
Multiplied by 3x and 7.
Multiply by 3x to the 7. So we come in here, multiply by 3x to the 7. So we're going to have 3x to the
K plus 7.
k plus 7.
K plus 7.
Right? If we multiply x to the k times, if we multiply those two together, you add the exponents. And we still have a division by k. So all we did was multiply the inside by 3x to the 7. Does that change the interval of convergence? No. So that's, so far, no endpoint testing. When you do the substitution, you have to modify the interval. When you multiply by a power of x, it doesn't matter. It doesn't change anything. You can imagine doing the ratio test. If you do a sub k plus 1 over a sub k, the extra x's just cancel.
I mean, you should have tested for the last one.
No, for substitution, you don't have to test at all. So for so the 3 things, substitution, no testing at all. Great, but you have to modify it. Power of x, you do nothing. So that's the simplest case. You don't even have to modify it. And then derivatives. These ones we have to modify. This is the hardest one. This is the one that always is the toughest on the test. So find the power series representation for G by differentiating or integrating the power series for F. So first off, let's make sure we understand the power series for F. We know the geometric series. Right? The geometric series is
1 plus 1 minus or 1 plus?
1 over 1 minus x. the x to the k.
Just x to the k. Right, that's the geometric series, x to the k. Right? The geometric series is just those powers of x. And as long as that x is less than 1 in magnitude, it's going to add up to 1 over 1 minus x. And so our radius of convergence is 1, and the interval of convergence is that. Okay, so that's where we're starting. This power series, all we did was replace the x with
5x squared.
close.
-5.
Negative 5x squared. This will still start at 0. So that is this power series. We could simplify that if we wanted, don't need to. But the IOC for this one, we have to come over here and say, okay, well, this is where we started, but we replaced the x with negative 5x squared. So now we have to come through here and modify it. So certainly we know how to divide by negative 5. When we do that, we have to reverse the inequality. So we get that. Let's write it more legibly. In other words, we read from left to right, so let's change it so that it looks like we would think of a number line. Negatives on the left, positives on the right. And here's where we have to use our little clever algebra tool. We know that x squared, no matter what x is, it's always bigger than this negative 1/5, no matter what. So really, the only consideration is that. And that, the x's that satisfy that are the same x's that satisfy the one before it. Now we can do this whole square root business. But the square root of x squared is not x, it's absolute x. We have that. This tells us two things. This tells us the radius of convergence is 1 over root 5, and it tells us that the interval of convergence is going to have boundary points that look like that. Do we have to test these endpoints?
Probably should, but.
No.
No, we don't have to test them because we just did substitution.
Oh, right, this was substitution.
Substitution you don't have to test. That's great. That's great. So we don't have to test these endpoints, so they stay soft. Now, we need to know how to get to G from F. How do we get to G from F? Are we going to integrate or are we going to differentiate? So if we think about integration, so I agree we are going to differentiate, just think about in your mind, because sometimes it's not going to be obvious. If you integrated this, what would you end up with in general?
Water.
A what?
Water.
Nope.
Oh. Oh,
No
was it
X.
arctan?
Arctan.
Arctan.
So there's a 5 here, but that just modifies things a little bit. If this was 1 over 1 plus x squared, that is the derivative of arctan. So if you were to integrate this, you'd get some modified arctan. So that right away says, oh, we must have to differentiate, even if it's not obvious. If you can at least in your mind say, oh yeah, if we integrate this, we're going to get an arctan, so that's out of the question, so we must be differentiating. So let's check. So we're going to write f in an easier, in a way that's easier to differentiate. I don't want to do that rule, quotient rule. So the derivative here, bring down the negative 1, subtract 1, multiply by the derivative of the base. So we've got that. Oh, we're super close already. This has a square in the denominator. This is actually a square in the denominator. So let's rewrite this without negative exponents. So negative 10x over 1 plus 5x squared quantity squared. So we have that. So we are super close. We are super close. So g of x is equal to x over 1 plus 5x squared squared, which is going to be f prime of x modified how?
Negative 10.
Say that again?
Divide by negative 10.
Not divide.
Multiplied by 1/10.
Multiplied by the negative 10, right? Because this right here, I can get all the way there, right? That is g right there.
So yeah, don't we divide it by negative?
Oh, I'm sorry. Yeah, I got you. Sorry. Yeah.
It's g of x times.
No, you're right. My bad. So if we divide out the negative 10, it matches. Here is f prime of x. If we divide this away, if we divide that away, then it's g, right? There's g. So g is this whole thing divided out the negative 10.
So f prime of x equal to negative 10 g of x.
Yes.
So you divide.
Yeah, exactly. And that's what I was thinking in my mind, that if you factor out this negative 10 here, then you're left with this expression, which is g. So you can think of f prime of x is equal to negative 10 times g of x, but what we want is to isolate g. We want to know what g is equal to. What do we have to do to f to get to g? So there's g. We take f prime, and if we divide out the negative 10, then it matches. So that is our formula that tells us how to get to g from f. So therefore, this implies that g of x is equal to negative 1/10 summation. So we come up to the summation for f. We need to differentiate that summation. So f prime of x, we come over here, f prime of x, we bring down the k. So it's going to be k, leave the base alone. What do we do to the exponent? Subtract 1. And then we use the chain rule. So power down, subtract 1, multiplied by negative 10x. Okay, and now we have to ask ourselves, does it still start at 0, or does k start at a different number? And when you look up here, if you put in a k equals 0, you would have a negative 1 exponent, which is going to shove x's into the denominator, which is not what a polynomial looks like. A polynomial has integer powers of x, positive integer powers. So k must start at 1. And it's just in your mind, if you just think about this, like 1 plus x squared, if you take this derivative, you lost a term. If every term is represented, and you take, including the constant, if you take the derivative, you lose a term. And that's the idea here. We lost a term. It's going to start at 1 instead of 0. All right, so there's our derivative. Okay, so that is what's going to go down here. So we have negative 1/10 times f prime. I'm going to have to shrink that for a minute. So f prime is going to be, let's see, k multiplied by negative 5x squared raised to the k minus 1, all multiplied by negative 10x. So there's g.
Negative 10 and negative 10.
We can factor out this negative 10. That negative 10 right there, that's going to cancel with this negative 10. Those will cancel. And so let's see. And there's no other constants that can combine. We'll talk about where it, well, we already did, right? This we said starts at 1. So this should start at 1. Go to infinity, starts at 1. You can just put a 1. I know what that means. Here we're going to write this as k times x multiplied by we don't have to, unravel all this stuff. It's totally fine to leave it unsimplified. There is the power series for g of x. Power series for f prime divided by -10. There it is. So that's great. Now we have the power series, but with every power series comes an IOC. We need to know what's the interval of convergence. The nice thing about derivatives and integrals is that the boundary points don't change. We know the endpoints of the interval are going to match the endpoints for f prime up here, for f actually. So it's what did I just say? I think what I just said was wrong. So the interval of convergence that we got for our, oh no, I said that right. The interval of convergence for f, this was not f. So the interval of convergence for f, we will have the same interval of convergence for its derivative, except maybe we have to include or exclude endpoints.
And then multiplying by a constant like -1/10 doesn't change it.
Doesn't change endpoints. And again, if you think of the ratio test, there would be
1 to 1.
You're figuring out that K above,
this one right here,
up a little, just yeah.
that.
Is it an oversimplification, say you like subtracted 1 inside, so you have to add 1 to the outside?
No,
Okay.
yeah, that's fine. You know, the idea if the constant term is there, when you differentiate, it vanishes. So you have an extra term there, you lose a term there. It doesn't. Yeah, it's always going to be that way. So if something makes sense to you like that, that you're losing something here, so you're gaining something there, that's fine. Okay, but now with the nasty piece, we have to test the endpoints. So we have to test each of those endpoints. This is always the pain. Okay, so we want to test x equals -1 over square root of 5. So that means we have this series starts at 1. We're replacing all the x's that we see with -1 divided by root 5. And it's often just a bear. It's usually just algebra, but it's generally a pain. You just have to be super careful. So let's just leave this part alone for the moment. Let's simplify what's in there. That looks to be where the mess is. So this, if you square this, you will get 1/5. Everyone agree? The square of that is 1/5. Well, then the 5's cancel. So the only thing left in here is a -1.
I've got an alternating series.
Say again?
I've got an alternating series.
And we can combine these though.
Oh.
Right, so we have -1 there and -1 there. Now sometimes you can't combine, but in this case we can combine, right? We have powers with the same base. So we're going to end up with -1 to the 1 multiplied by this, so that's -1 to the k. So we do end up with a truly alternating series, and we have k over root 5. And that starts at k equals 1. Everyone okay with that? You're thinking of this as -1 to the 1. So you have powers with the same base, you add the exponents, 1 minus 1 is 0, so you end up with an exponent of just k. Okay, does that converge or diverge? Diverge. That is an alternating series.
That does not go to 0.
This is a sub k. Alternating series, a sub k doesn't include the switch. And what is the limit of a sub k in this case? So the limit of a sub k as k goes to infinity is the limit of this as k goes to infinity, which is infinity. This is not equal to 0. So what test is it that's telling us that this diverges? Divergence test. So therefore diverge by the divergence test. Now the other endpoint is actually going to be pretty easy. The only difference when we plug in this endpoint is that this is positive here, right? Doesn't that just, it's 1 over root 5, positive 1 over root 5. So then when we square it, we get 1/5 again. So we actually end up with the exact same series. Everyone agree?
K plus 1 on the negative instead, because on the outside it's K over root. So you can't do the combining -1 with the -1 to the K minus 1, because you have 1/5 instead of -1/5.
Yeah, but it is one.
But this in here is identical, right?
On the inside it's identical, but on the outside.
Why does that change?
Not that one, even further out, that one is now positive.
Why is that positive?
Because we're plugging in
We're plugging in
1/5,
1/5.
not -1/5.
We're plugging in one.
Oh, because that was an X.
That was.
Oh, thank you.
So it's.
Yeah. Gotcha. I thought that, I just saw that as a constant and was thinking that was the only X.
No.
Gotcha. Thank you. Yeah, let me rewrite that then more completely. So then it's K. This one is positive.
Yeah.
I was just so obsessed with focusing on the inside here. That's going to be positive 1/5 when we square it, so we get that. K minus 1. Yeah, so the difference is that we,
Just switches, just offset by 1.
the switch is going to still be there. So this is going to be -1 to the K minus 1. Yeah. And then we have K over root 5. So the only difference is the switch is offset by 1, but the A sub K's are identical.
Yeah.
That's your A sub K, and same as that. So same conclusion here. So therefore, the interval of convergence is going to go from -1 over square root of 5 to positive 1 over square root of 5. We did not gain any convergence at the endpoints.
Since we took a derivative, that's kind of what we expected. It's really only gaining if it, like, we integrate.
Yeah, usually derivatives are going to lose convergence, integrals will gain. Yeah. So if we didn't have it to begin with, it is exactly what we expected.
Is it always that case?
I have not seen it be any other way, but I haven't dug into it in any super depth. So let's go to a binomial. Make sure we do a binomial. This one's a fast one, so let's do this one first. So, maybe I shouldn't say fast, but. Okay, so the binomial expansion, so find the binomial expansion for this function. So the p-value is 1/2. So for a binomial, p is the exponent on 1 plus x, different from the p-series. And I need to give you the interval. The interval, we can't figure it out in this class. So first, we want to know what the power series, what the binomial expansion or power series is for that. So what we want to think about is 1/2 as the exponent. And that's always going to be in the upper position of the binomial expansion here. So the coefficients are going to look like this. So it's always going to be geometric series like 1 plus x squared plus x cubed, etc. But instead of 1s as the coefficients, we have these modified coefficients. So you should think of it like a geometric series with modified coefficients.
Will it always start with a 1 then?
Yeah,
Okay.
unless there's a constant multiplied out in front.
Okay.
Yep, always. So it's going to be, this will always be 1. This is always going to be 1/2.
Yep.
And then we usually are going to ask for 4 non-zero terms. So we have to come over here and calculate 1/2 choose 2. And so for that, we're going to get -1/8. So we start with the half, so that matches. And then we subtract 1, and we keep subtracting 1 until we get to this number of factors. So we have 2 factors. Okay, and then that's -1/4 divided by 2, which is -1/8. So that tells us that this is going to be -1/8 x squared. And then to get to the next one, we have to do a half choose 3. So same idea, we start at 1/2, we do repeated subtraction by 1 until we get to 3 factors. So in the numerator, we're going to have 3/8. In the denominator, we have 6. And so that's all going to simplify to,
1/16.
so, yeah, 1/16? I think so. I think so.
1/8 over 2.
Yeah, 1/8 over, yeah, so that's, we're going to multiply 3/8 times 1/6, so we cancel out a 3, so we have a 2 in the denominator. And that's going to be our 4th non-zero term. So there is the power series for this. And the interval of convergence is right there. It's given. So the interval of convergence for this one, we include the endpoints. Now, okay, so we'll call that F. Now it says, how about the power series for G? Well, how do we get to the power series for G from a F? Sub.
Yeah, times by -4.
So we're going to replace, so you should think of it as replacing the x with -4x. So we're going to replace all these x's with -4x. So this is going to be 1/2, replace that with -4x. Minus 1/8, replace that x with -4x. Plus 1/16, replace that x with -4x. Cubed, minus etc. You don't have to simplify this. I'm totally fine if you don't simplify it. When it's simple enough to do it, it's not bad to do it, but I will not take off points if you don't simplify this. There's bigger, more important things. How do we modify the IOC?
Plug in
More.
So we have -1. We include the exponent here, so this is what our new IOC interval looks like. We divide everything by -4, which means switch the inequality. And therefore, the new interval of convergence is -1/4 to 1/4, including the exponents. And with that substitution, we don't have to deal with any endpoint testing. Substitution, good to go. Multiplying by x, good to go. It's only if you differentiate.
And would you want us to also put R for these ones, or just I?
Just I is fine. Yeah, unless it asks you for R,
Just do I?
yeah, just do I.
Okay.
All right, any questions on any of those steps? Definitely practice the binomial, because it really is an easy problem overall. It's just a question of getting some of this arithmetic right. But it always looks the same. P choose 0, P choose 1, P choose 2, 1, x squared, x cubed. So it's really, it's a fairly quick problem to deal with it. All right, let's do one of these where we are going to approximate an integral. So we've got a power series that's given to us with its interval of convergence. We're doing a slight modification. The modification is just that we replace x with x to the 4th. So we don't have to change, we just have to modify. We don't have to test endpoints. So this is going to be integral 0 to 0.3. And we're taking this power series, replacing x with x to the 4th. And here it's going to make sense to simplify those powers when you plug in x to the 4th. Because we have to integrate. So if we started with this inequality, and we replaced the x with x to the 4th, that's what we have to worry about. So it's always greater than -1, so the part of this that matters is that. Then we can take the 4th root of both sides. The 4th root of x to the 4th is absolute x So this tells us that the interval of convergence now includes both endpoints.
Oh, because, yeah, usually with an integral it adds, right?
We didn't integrate though.
Okay.
Right, so all we do is a substitution, and this substitution, because of the way the fourth root works, ends up giving us the inclusion at both endpoints.
So you ignore the
Yeah,
left
yeah,
side.
the left.
Ignore the left side now. Okay, so that's our new IOC for this series right here. Now we're integrating. And so now when we integrate, we are going to have to test endpoints. And these are both already included, so we're probably not going to have anything change. So we just integrate. Add 1 to the exponent. Divide by the new exponent. So there's our integral, our antiderivative. We're going 0 to 0.3. 0 doesn't give us anything. 0.3, let's see. So we end up with 0.3 minus 1/10, 0.3 raised to the 5th, plus 3/72. That can be simplified. That's going to be 1/24, 0.3 to the 9. And then 5 divided by whatever 13 times 16 is. 0.3 raised to the 13 plus etc.
208.
208, thank you. All right, so there is our series. And let's go back to the instructions. Use the series to estimate the integral's value with an error of less than 10 to the negative 3. So here's where we have to look at our calculator. This is plus, minus, plus, minus, plus, so it's alternating. So we just have to find the first term that's less than 10 to the negative 3 and add everything up in front of it. So we need to know which term is less than 10 to the negative 3.
The second one,
This one right here? Is it already less right there?
because that's point.
C'est possible.
2 to the negative 4. Yeah.
Yes. So do we agree that that term is less?
Point 3. Good math, guys.
Good math. So this, less than 10 to the negative 3. Therefore, our conclusion is that that whole integral is approximately equal to 0.3. So if we call that integral whatever, let's call it gamma. No, omega.
And would you want to write like 0.300 to show the accuracy level, or?
I don't care. This is math,
Not physics?
chemistry.
Not physics, chemistry, none of that?
No significant
Sig figs?
Sig figs.
Sig
My
figs.
math class?
The calculator
Who
told me
cares
this,
about
but
sig
that's
figs?
how we do
Who
it.
cares about sig pigs? I didn't say that. Yeah, so that's the idea, alternating series. So this alternating series remainder thing is super important because it's part of a lot of different types of problems. All right, see you on test day. See you on Thursday.
But I know how to intimidate in class. What if, I mean, you,
Did you say you're going to intimidate the class? Is that what you said? You?
no, you the
I'm
teacher.
rather quick.
Oh, it's here.
Well, what if, on a random day,
Yeah.
you set up desks like this? And,
Wait a second.
and also not only that, but put
No.
boxes on each.
Final answer.
Shoe boxes on you.
Mr. Boss, are we allowed to filibuster the test?
Filibuster?
Can we?
This is math.
Don't care.
Are we allowed to filibuster it?
No filibustering allowed.
I'll pull up with a
You
whole
can-
calculus textbook. I'll read every
You
single
can-
piece.
you
What
can-
about, or emotional support fund with internet connection?
The emotional.
What about, yeah, emotional support.
The
that's what-
emotional